Chapter 3, Part 4, Newman Projections. There is free rotation around single bonds, or sigma bonds. Alkanes can exist in different configurations, also known as conformers, but this does not change the identity of the compound. Let's look at these structures below and determine if they are the same compound or different. So you can use the process that we use for IUPAC nomenclature to try and figure out if these compounds are the same or if they're different. If they're the same, it'll be because there's some sort of rotation around one of the single bonds, and we're just looking at it in a different conformation. So what I would do is look for the longest carbon chain. So I see 1, 2, 3, 4, 5. And then I also see 1, 2, 3, 4, 5 in the second molecule. Now I would look for those substituents. There is a methyl group on carbon number 2 and a methyl group on carbon number 3. And I see the same substituents on the next molecule. So these are the same molecules. This particular example just has one of the molecules rotated on the paper. You could also look at it as like a rotation around a single bond, but it really is just if you took the molecule and rotated it 90 degrees clockwise, this one, you would end up with this structure here. Now let's look at this example. Go ahead and pause and take a second and see if you can figure it out for yourself. Okay, so the longest carbon chain that I see starts here. 1, 2, 3, 4, 5, 6. And then on the next molecule, I'm going to start numbering from the right because that's closest to the substituents. 1, 2, 3, 4, 5, 6. So they both have 6 carbon chains. The first one has substituents, methyl substituents on carbons 3 and 4. The second one has methyl substituents on carbons 2 and 4. So these are not the same molecule. These two are the same. Not the same. So these are not conformers of each other, but rather different molecules entirely. One tool that we can use to better understand these conformations and rotations around single bonds is to use a Newman projection. Newman projections focus on one carbon-carbon bond and the energy that is required to rotate around the bond. There is energy required to rotate because each of these atoms has to pass by another atom. And remember, we're looking at these as little letters on little sticks, but each of these has a significant electron cloud. So having those electron clouds pass by each other does actually take a significant amount of energy, and that can slow down the rotation of a sigma bond. Since these are all just hydrogen groups, it's pretty safe to assume that there is pretty constant rotation around these single bonds. So a Newman projection starts with a circle. And then you draw kind of a Mercedes symbol, like so. And what this symbol represents is actually these bonds. And we are looking at this molecule from the side. Here's my eyeball, looking at it this way, so that ultimately the two carbon atoms are overlapping each other. That overlap is pictured right here. If you were to take a pencil and draw this dot on your screen, your pencil would be going right through the bond that we're analyzing, which is this one. So on this front bond, we can put H1. H2 would be on the left because it's pointing backwards in our original image. And then H3 would be on the right because it would be coming towards us. And then to represent our atoms on the back carbon, we have to get a little creative. This circle that we drew as our first step is actually there to help create this like sense of 3D-ness. So we are going to draw lines coming out from behind the circle, but they do not go through the circle. They are behind it. And this tells us that these bonds are the bonds coming off of the back carbon. And then HA would be down here because it is opposite of H1 and on the same plane as H1. HB and H3 are both on wedge dashes, so they're both coming towards us. So HB should be on top of H3. And that means that HC is on top of H2. So this is the Newman projection. It's important to know also that we always talk about how carbon makes 4 bonds. And looking at this, you're only seeing 3 bonds really obviously highlighted. Again, that's because the bond that connects the 2 carbons is going through this blue dot right here. So it's not really pictured because it's overlapping. And what we are focusing on are the 3 things that are attached to that front carbon and the 3 things attached to that back carbon. In this case, just unexciting hydrogens. So this particular conformation has every single hydrogen atom perfectly spaced out. Nothing is overlapping. Everything has its space. This is called a staggered conformation. And this is going to be our most stable conformation because it is our lowest energy conformation. If you recall from Vesper theory, you learned that electron pairs repel each other, electron clouds repel each other. So everything likes to have its own space, and when it does have its own space, that's going to be preferable and lower energy. Now, this molecule here is the same molecule, but we rotated our back carbon 180 degrees. So we took this HA and went whoop and flipped it up to the top, and HB and HC came with it. So to draw the Newman projection of this one, I didn't leave myself a lot of space, so I'm going to draw it off to the side here. I'm going to start the same way. I'm going to use my little Mercedes sign to indicate these 3 bonds. And I did not do anything to that first carbon as far as rotation goes. So H1, H2, and H3 are all in the same place. Now, these hydrogens are no longer staggered. They're actually on top of each other. If our eyeball is over here, looking at the molecule this way, then H1 would be eclipsing HA. So I'm going to draw a line kind of just behind it. Whoops, I'm going to move the 1 up here and make this part of my H. So HA is just behind H1. Of course, the way I drew it, it's not perfectly behind it, but we have to be able to read it. And in this image, HB ends up behind H2. So I'm going to draw a line just a little off of H2 and plug in HB. And then HC is directly behind H3. So I'm going to do the same thing. I'm going to take a line that's just a little off and plug in HC. So this conformation is different from the one on top. This is what's called an eclipsed conformation. This is the least stable conformation because it's going to be much higher energy. Now again, we are looking at hydrogen atoms. This is just simply ethane. There's not a lot of really interesting stuff going on here. So as far as energy levels, this is not that dramatic. It's just hydrogens eclipsing each other. But as far as ethane goes, this would be the worst case scenario as far as energy levels in a rotation. And this would be our best case scenario. So let's go through a process of how to create our own Newman projections, and then we'll do some practice problems. So the first thing you need to do is identify the bond that you are focusing on. In the previous example, it was easy to do that because there was one carbon-carbon bond, so we couldn't really get all that creative. And then you sketch the Newman projection template. Any question that you're answering will have some sort of prompt about the lowest energy conformation, the highest energy conformation. It may say most stable, least stable. So you're going to have to make a decision ahead of time of whether you're going to draw a staggered or eclipsed conformation. And I would go ahead and sketch that Newman projection template out entirely with all the bonds. And then you want to identify the 3 things that are attached to each carbon. It's very unlikely that I'm going to ask you to draw the Newman projections of ethane because ethane is just a bunch of hydrogens. So it's going to be like methyl groups, ethyl groups, it could be anything. And then you're going to place those 3 things on the bonds that you've drawn. If you're aiming for the most stable, the lowest energy, you want to try to keep your largest items as far apart as possible. And if you're aiming for the least stable, the highest energy, you want to make sure that all the worst possible things are happening. So the largest items are overlapping each other as much as possible. And we'll look at that in our examples. Remember to check that you're not breaking any bonding rules and count your carbons to make sure you have drawn the correct structure. The number of Newman projections that I have graded that have way too many sticks is just astounding. So stick to the template that I gave you on the previous page and draw that first so that you don't end up going a little crazy trying to figure it out. So we're going to start with a simple practice problem. Provide the most stable and least stable conformations of butane, looking down the 2,3 carbon-carbon bond. So the first thing that we need to do is draw butane. Butane is just 4 carbons. Whoops, let's connect those like that. And this is saying that we're looking down at the 2,3 carbon-carbon bond. So this is carbon number 2, and this is carbon number 3. The next thing we need to do is identify the 3 things that are attached to each carbon. Let me relocate my labels so I can draw those other things. So carbon number 2 is going to be my front carbon, and carbon number 3 is going to be my back carbon. And we're going to draw the most stable and the least stable conformations. So let's go ahead and draw our templates. I need a circle, I need a front carbon, and I need a back carbon. This will be my most stable conformation because it's staggered. And then for my least stable conformation, I'm going to need an eclipsed template. So I'm just going to go ahead and draw my eclipsed template. Your lines don't have to be exactly the same as mine. It's just you want these 2 things to be close together and very obviously not staggered. If you kind of draw it over here, I may not really know what you're aiming for. So just kind of keep them close together. So this is the least stable conformation. Okay, so the next thing is we need to identify those 3 things attached to each carbon atom. So butane is a symmetric molecule, so we're going to have the same 3 things on each of these guys. So one thing that's attached to carbon number 2 is the methyl group that is carbon number 1, right? And carbon number 3 also has that. That's carbon number 4. But the other things that they have are not drawn for us. They are implied, and those are the hydrogens. So carbon number 2 has a methyl group and 2 hydrogens. Now you could go ahead and just draw those on your Newman projection. It doesn't really matter where you put your items for the front carbon. What matters is the relative positions that you put the stuff for the back carbon in, or vice versa. You could start with the back carbon and then put things on the front carbon. It wouldn't really matter. So then we need to do the same thing for carbon number 3. We have our 2 hydrogens and our methyl group. So for the most stable conformation, I want to make sure that my largest items are as far apart as possible. I have a methyl group and 2 hydrogens. The methyl group is my big piece. So I don't want to put it here and I don't want to put it here because those are the closest possible positions to the other methyl group. I'm going to put it here because that gives it the most space relative to the methyl group. And this is going to be the lowest energy conformation. For my least stable conformation, I want to do the exact opposite. I still have to place those same 3 items on these bonds, but I want to make my molecule as uncomfortable as it possibly can be. So I'm going to put my methyl group here, right behind my other methyl group, and then put my hydrogens here. Now, if you're looking online and you're following along with an Organic 1 class, then what you might find is that they also talk about some other types of conformations. They might mention like gauche and anti. Those are outside of the realms of this class. We are just looking at simply the most stable, the best case scenario, and the least stable, the absolute worst case scenario. So these are our conformations for butane, looking down the 2,3 carbon-carbon bond. On this next page, I've given you a molecule, and I'm asking for 3 different Newman projections. So let's go ahead and just number these 1, 2, and 3, and we'll leave space for those here. 1, 2, and 3. Number 1 says the most stable conformation, so I'm going to go ahead and do myself a favor and draw a staggered conformation. Number 2 says the least stable, so I'm going to go ahead and draw an eclipsed conformation. So I don't want to make any mistakes by, failing to read this correctly later. And then number 3 says the most stable. So another staggered. Okay, so you might be wondering, I asked for the most stable twice, but they're looking down 2 different carbon-carbon bonds. So the first one, I'm asking for the 2,3 carbon-carbon bond. The second one, I'm looking down the 3,4 carbon-carbon bond. So we're going to have to analyze our carbons twice. So let's start with just looking at that 2,3 carbon-carbon bond. So anytime I give you specific numbers like this, I'm asking you to use IUPAC rules for choosing those numbers. So IUPAC rules say that I need to start numbering closest to the substituent. So that would make this carbon number 1. Oops, there we go. 1, 2, 3, 4, and 5, right? So carbons number 2 and 3 are the ones that we're analyzing. The next thing that I would do is go ahead and plug in any missing atoms, so just hydrogens. So carbon number 2 should have another hydrogen, and so should carbon number 3. And now I need to choose my 3 items. Typically I like to highlight them just to make it really, really easy for me to see what I'm doing. So I'm looking down this 2,3 carbon-carbon bond, right? My 3 things on carbon number 2 are a methyl group, a hydrogen, and a methyl group. So just like in my last problem, I'm going to go ahead and plug those in on my front carbon because it doesn't really matter where I put them as long as I arrange my back carbons correctly. So I need 1 hydrogen and I need 2 methyl groups, 1 here and 1 here. You could also leave those sticks blank, like a line bond structure. I'll do that on number 3. So number 3, I'm going to write out my hydrogen explicitly, but I'm just going to leave these blank because a blank stick indicates a methyl group. Oh, whoops, I just realized number 3 is a 3,4 carbon-carbon bond. I meant to do this on number 2. So I'm going to leave these 2 sticks blank to represent my methyls. So then on carbon number 3, I have a methyl, a hydrogen, and an ethyl group. So on structure number 1, I'm aiming for the most stable conformation. And I'm going to go ahead and place my largest thing first because that will help me not make any mistakes. So my largest item is the ethyl group. And notice also this structure doesn't have any dashes and wedges indicated. So there are no rules about which direction or whether the ethyl group and the methyl group are clockwise or counterclockwise from each other. So you can just kind of do that willy-nilly. There's only one place on our structure number 1 that we cannot put the ethyl group, and that's right here in between the methyls. This place is the most congested, and that is the last place we would want to put the ethyl group. So my ethyl group is going to go over here. So I can draw that in a line bond structure like I just did, or if you want to write it out, you can write out CH2CH3. Now I have my methyl and my hydrogen left. Hydrogen is my smallest thing, so I'm going to go ahead and put this here in between my methyls because that's going to be the least offensive to my 2 methyls. and I'm going to put my other methyl group over here. So this is my most stable conformation. I have given everything as much space as I possibly can by keeping my bigger groups out of the most congested space. Now let's look at our eclipsed conformation. Here, we want to make everything as bad as it possibly can be. So I'm going to put my small group behind my other small group, and then I'm going to focus my big groups behind my methyls. So this one, I'm going to turn into my ethyl. So I'm just going to do that using line bond structures. And then this one will be my methyl group. So I'm just going to leave it blank. So this is representing all the same groups that are over here. I've just drawn it out in line bond format so that you can see what that would look like if you chose to do it that way. Okay, in my next example, I have the most stable conformation looking down the 3,4 carbon-carbon bond. So let's go ahead and erase all this extra stuff that I added on to here. Gotta be careful because, oh, you know what? I didn't draw that out in pencil, so I can just erase whatever I want. Excellent. Okay, so now I'm looking at the 3,4 carbon-carbon bond. Okay, so my eyeball is now coming from here. And I need to plug in all the missing things from carbon number 4. So carbon number 4 actually should have 2 hydrogens as well. So let's go ahead and give those to carbon number 4. So let's highlight our 3 things that are attached to each carbon. So carbon number 3 has this large isopropyl group. It also has this methyl group and a hydrogen. Carbon number 4 has 2 hydrogens and a methyl. So these are the things that we need to somehow fit onto these sticks. So let's start with carbon number 3. I'm going to draw my isopropyl group out like this. So this is carbon number 2, carbon number 1, and then the methyl group coming off of carbon number 2, in case you were having a hard time tracking that. And then carbon number 3 also has a methyl group on it, so I'm just going to leave one of these sticks blank. And then it also has a hydrogen. And then carbon number 4 is behind it, and this is the most stable conformation. So I want to make sure that my biggest thing on carbon number 4 is very far away from this. And my biggest thing on carbon number 4 is my methyl group. So I'm going to put that here. And then my hydrogens will go here. So that is how you do Newman projections. This is kind of a new concept to us and kind of a bigger concept. So if this is something we need to practice a lot more in class, please let me know if you have any additional questions.